In the last module, we had just started we defined turbulence, and we had introduced the concept of fluctuating component and the mean motion. So these two we had introduced, and we had time averaged the incompressible flow continuity equation, and we had got this one, that is del u by del x, del u bar by del x plus del v bar by del y plus del w bar by del z equal to 0. There is nothing new, it is the same. The equation looks the same. Now let us take the x momentum equation. So let's write the x momentum equation. So the x momentum equation is rho del u by del t plus u del u by del x plus v del u by del y plus w del u by del z is equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared. So you get, this is it. So now let us replace u with u bar plus u prime, v with v bar plus v prime, and w with w bar plus w prime, and p with p bar plus p prime, and time average. So we are time averaging the momentum equation. This is also called Reynolds averaging, because the Reynolds have apparently had done for the first time. So, but before I do, I need to rearrange this little. So rho into del u by del t plus del u squared by del x plus del of uv by del y plus del uw by del z is equal to minus of del p by del x plus mu del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared. So this is the same as this. Actually, if you expand this, continuity equation comes, so you will end up getting this only. You can check it out yourself. So if I time average this, what will I get? Del u bar plus u prime bar by del t, you are going to get del u bar by del t plus del u prime bar by del t. This term is 0, this vanishes, so you get del u bar by del t. But I am considering steady mean flow, that is, if I put a pitot tube and I am seeing my manometer, my manometric value is not changing, so then in that case this is the mean component, that is u bar, doesn't vary with time. So that is del u bar by del t equal to 0. If it is unsteady, if the flow itself is unsteady, you will never get u bar, del u bar as 0, that is del u bar by del t as 0. But we are considering steady mean flow. Now the next term, del u squared bar by del x equal to del of u prime, u bar plus u prime whole squared bar by del x equal to, you get del u bar squared by del x plus del u prime squared bar by del x plus you are going to get del u bar u prime bar by del x. We have seen that if you time average u prime bar, you are going to get 0. So this term is going to be 0. So I write this as 2u bar del u bar by del x, I have just taken this out, plus del u prime squared bar by del x. So this is what I get when I time average del u squared bar by del x. Next term is del of uv bar by del y, that is del of u bar plus u prime into v bar plus v prime bar upon del y. If you recollect, we had just done this u bar plus u prime. If you recollect here, u v bar, if when we are done, we ended up getting only u bar v bar plus u prime v prime bar. So you will get here as del of u bar v bar plus by del y plus u prime v prime bar. If you still want to write, you can write this as u prime v bar bar plus u bar v prime bar, just for the sake of completeness. This term will be 0, this term will be 0. So you get del of, I will expand this. So you get u bar del v bar by del y plus v bar del u bar by del y plus del of u prime v prime bar by del y. Okay. So similarly, without doing, I can write directly del u w bar by del z equal to u bar del w bar by del z plus w bar del u bar by del z plus del u prime w prime bar by del z. So that completes the left hand side, all the terms we have completed. Similarly, I can write directly del p plus p bar plus p prime bar by del x equal to del p bar by del x, because del p prime is 0. Similarly, I can write del squared u by u bar plus u prime bar by del x squared equal to del squared u bar by del x squared, because u prime bar is going to be 0. So substituting all of this in my momentum equation, I will get rho into del u prime squared bar by del x plus 2 u bar del u bar by del x plus u bar del v bar by del y plus v bar del u bar by del y plus del u prime v prime bar by del y plus u bar del w bar by del z plus w bar del u bar by del z plus del u prime w prime bar by del z, this is left hand side, is equal to minus del p bar by del x plus mu into del squared u bar by del x squared plus del squared u bar by del y squared plus del squared u bar by del z squared. Now, if I rearrange this, I can write this as del of 1 u bar if I take common, del u bar by del x, one term of this, and then you have this one, this term if you take, plus del v bar by del y plus then you have this term, that is del w bar by del z if you take, plus you are left out with another term, that is u bar del u bar by del x plus v bar del u bar by del y plus w bar del u bar by del z is equal to, all the terms which are left out are this one, this one and this one. This I am pushing to the right hand side. So I get minus del p by del x plus mu del squared u bar by del x squared plus del squared u bar by del y squared plus del squared u bar by del z squared minus of rho del of u prime squared bar by del x plus del of u prime v prime bar by del y plus del of u prime w prime bar by del z. So let us write, similarly I can do for y and z momentum equation. So let me write for y momentum equation. So that is minus rho of, this has vanished, this is 0 by continuity. So now let me write all momentum equations. So rho into u bar del u bar by del x plus v bar del u bar by del y plus w bar del u bar by del z is equal to minus del p by del y plus mu del squared u bar, okay, minus of rho del of u prime squared bar by del x plus del u prime v prime bar by del y plus del u prime w prime bar by del z. Similarly, y momentum equation, rho of u bar del v bar by del x plus v bar del v bar by del y plus w bar del v bar by del z is equal to minus del p by, this was actually del x, del p by del x, sorry, this is p bar, del p bar by del y plus mu del squared v bar minus of rho, please note now, del u prime v prime bar by del x plus del v prime squared bar by del y plus del v prime w prime bar by del z. That was y momentum equation. Let's write z momentum equation, u bar del w bar by del x plus v bar del w bar by del y plus w bar del w bar by del z is equal to minus del p bar by del z plus mu del squared w bar minus rho del u prime w prime bar by del x plus del v prime w prime bar by del y plus del w prime squared bar by del z. Now what are these? So if you just see, if these equations are not there, only these left of my hand, if you see these equations, these were the equations which we were seeing earlier. These are the terms which have come additionally because of Reynolds averaging. So these terms can be visualized, that is this minus rho u prime squared bar minus rho u prime squared bar can be visualized as sigma xx prime, and minus rho u prime v prime bar can be visualized as sigma xy prime, and minus rho u prime w prime bar as sigma xz prime. So minus rho v prime squared bar as sigma yy prime and minus rho w prime squared bar as sigma zz prime. Prime represents additional shear stress, that is sigma, only one more thing is left out here, that is sigma yz prime is equal to minus rho v prime w prime bar. So what are these stresses? These stresses are additional stresses, that is sigma, that is you have sigma xx prime, sigma yy prime, sigma zz prime, sigma xy prime, sigma xz prime, sigma xy prime, sigma yz prime, sigma xz prime, sigma yz prime. So these these are the additional stresses in addition to our normal stresses. In fact, we had sigma xx, yy, zz and sigma xy, sigma xz, which we wrote in terms of viscosity and the derivatives of the velocities. So we wrote that is linear deformation and angular deformation. We put all of those. So these are called as additional stresses. Additional stresses. That is, they are also called as Reynolds stresses because these were first derived by Reynolds in 1895. Okay. So then there is one doubt which we will all of us get is this minus rho u prime v prime, is it really negative? Minus rho v u prime v prime, is it really negative? No, actually minus rho u prime v prime happens to be positive. So what is the physical significance? So if we see the slides, just consider a plane shear flow. Consider a plane shear flow where you have the velocity varying like this. This is y, this is x. So this is the velocity. Okay. So now u bar y and v and w are 0. Now you have du bar by dy greater than 0. Now let us say there is a transverse motion causes eddies to approach the layer y, that is there is a v bar greater than 0, that is it is moving from downward layer y to y plus l, let us say it is moving up. So you have v prime greater than 0, but now what is happening? Since they essentially, because u is increasing from when it is moving from y to y plus l, they essentially retain their original velocity u bar, so they end up with a negative u prime when you are moving with v prime. So you have v prime is positive but the u prime is negative. So minus rho u prime v prime is going to be positive. So to summarize, we have, if you have a positive v prime, you will have a negative u prime. If you have a negative v prime, you will have a positive u prime. So that is the, so essentially you mean that u prime v prime is negative, is non-zero. So minus rho u prime v prime is positive. Okay. So this, what is that? What is this? This is the turbulent shear stress. Turbulent shear stress over and above the viscous shear stress. What was my viscous shear stress? Tau mu equal to, or tau v equal to viscous mu del u bar by del y. This stress minus rho u prime v prime is the turbulent shear stress which is over and above the viscous stress. That means total tau, we can visualize that total tau is equal to tau laminar plus tau turbulent. What is tau laminar? Mu del u bar by del y minus rho u prime v prime bar. If it is laminar flow, or if it is laminar flow or laminar boundary layer, you will have tau turbulent 0 because u prime is 0, v prime is 0. There are no fluctuating components. Okay. So this, but if it is a turbulent boundary layer, if it is a turbulent boundary layer, if it is a turbulent boundary layer, you will have tau equal to, you can directly write it as tau turbulent, that is minus rho u prime v prime bar, because tau laminar will be very much smaller than tau turbulent. Okay. So this is, so what is that we understood is that because of Reynolds averaging, we can visualize that in a turbulent flow you have additional 6 additional shear stresses, that is sigma xx, sigma xy, sigma xz, yy and zz. These are called normal shears, normal turbulent stresses, and these are called shear turbulent stresses. Okay. So, these stresses have come additionally over and above what we had these terms. Okay. That is the summary what we understand in this. Now, let me introduce what is called universal velocity profile. Why is it called universal? Because this profile is valid for both internal flows and turbulent flows. Universal velocity profile. Let me take internal flow. If I take pipe flow and this is the center of the pipe, okay, the velocity profile would be, as we know, it would be a hat profile. So, you have, this is my profile, this is my velocity profile. So, you have three regions in this. One is, this region is 1, 2, 3, let us say. One is viscous sublayer. Two is overlap layer, or it is also called as buffer layer, not butter but buffer. 3 is outer layer, or it is also called turbulent layer. So, if I were to plot this stress, so this is my pipe wall, okay, and this is my R, capital R, this is how R goes and this is how Y goes, okay. So, this is my shear stress. At the center the shear stress is 0, but as you move nearer wall the shear stress is increasing, this is shear stress. But what is the laminar and the turbulent component? It will be something like this. That is, this is the laminar component, tau laminar, and this is tau turbulent. So, as you come nearer to the wall, laminar component is increasing. As you come away from the wall, turbulent component is increasing. That means, in the viscous sublayer, laminar shear stress is greater than turbulent shear stress, because in the viscous sublayer there are no fluctuating components. In the overlap layer, tau laminar is of the same order of tau turbulent, and in the turbulent layer you have tau laminar less than tau turbulent. That means tau turbulent is greater than tau. That means tau laminar is mu del u bar by del y, and tau turbulent is, just to give you the feel, minus rho u prime v prime bar. Okay. So, this is what we understand. Then what is universal velocity profile? Universal velocity profile is u plus 3 layers, no? For viscous sublayer it is u plus equal to y plus for y plus less than 5, and u plus equal to 5 log of y plus minus 3.05 for y plus greater than 5 to 30. This is viscous sublayer, this is buffer layer, this is turbulent layer, that is u plus equal to 2.5 log of y plus 5.5. So, what is u plus? U plus equal to u by u tau, and what is u tau? U tau equal to square root of tau wall by rho. What is y plus? Y plus equal to y u tau by nu. You see what is the unit of u tau? What is the unit of u tau? U tau unit is, u tau is equal to square root of tau wall by rho. So, that is tau wall is What is the unit of tau wall? Pascal, that is Newton per meter square upon kg per meter cube. So that is Newton is kg meter per second squared per meter squared into meter cube per kg, square root of this. What is that I am going to get? Kg gets cancelled out. So I get it, this is of the order of meters per second. So u tau is called frictional velocity. U tau is called frictional velocity. You notice that now u plus is non-dimensional because it is u by u tau. What about y plus? Is it non-dimensional? Y plus is equal to y u tau by nu, that is y is meter, u tau is meters per second, nu is meter squared per second. So this is also dimensionless. Without derivation I have stated this. This is what is called universal velocity profile. But then these constants have come from experiments. In the next module I will show you how these have come from experiments. So in the slides, if you just see here, u plus versus y plus we have plotted. So in this here you can see that the experimental data matches well. In the viscous sublayer it is linearly varying, u plus is varying linearly with y plus, and in the buffer layer it is 5 log of y plus minus 3.05, and in the turbulent layer it is 5 log of y plus plus 5.5. In the next module what we shall do is we shall take up energy equation and time average the energy equation and see what all additional terms we are going to get. Okay, so with this we have in today's class, in today's module we have time averaged and found that the main takeaway from this module is that we have found additional stresses. These additional stresses are the normal turbulent stresses and the shear turbulent stresses. So the total stress is going to be laminar plus tau is laminar plus turbulent. So this is what is the major takeaway from this module. Thank you.